All right, so a little bit of background in case you have forgotten. We were discussing output stages, and we said that we need a stage which specializes in interfacing with the load resistance. It has the ability to drive low resistance load, and also if there is a heavy capacitive load as well. And what we are looking for in an output stage is basically a good swing, rail to rail swing here. The output voltage should be able to go to plus 3.3 and minus 3.3 here, the positive and the negative supply rails here. We need low output resistance, and of course we need low distortion, and preferably this stage should be a high bandwidth stage so that the overall bandwidth is not limited by it. And further, we require that the efficiency of this particular stage is high so that the power that is delivered to the load is not much smaller than the power which is actually taken. So what we are looking for is whatever power is taken from the supply is delivered to the load, right? So we're looking for an efficient amplifier. And in that context, we had seen the following. We had seen a common source amplifier and with the resistive load. And we had seen that this particular amplifier has suffers from distortion. And also we had seen that if you try to get a large swing, let's say plus 3 and minus 3, it ends up requiring a very large current. And obviously then the efficiency is also very low. And we also saw that the resistive biasing or the resistive RD that you see here is not suitable. What we can do is replace RD by an active load here, and that cuts down the kind of current requirement. So instead of requiring, let's say for plus 3 and minus 3, 33 milliamperes here, maybe you require only 3.3 milliamperes here. So the current requirements comes down by a factor of 10. So we said this is a much better stage. If you want to drive loads, this requires much less bias current as compared to this particular stage here. And the linearity of this particular stage is also better. And swing, of course, we know this is a common source stage here, so it gives a swing within VD sat of positive and negative supply rails here. So that was common source amplifier. And we had also discussed common drain amplifier. We said common drain amplifier is suitable for getting low output resistance because you're looking into the source here. And same thing, if you bias it using a resistance here, the current requirements are very large. Same, you require, for example, plus 3 and minus 3, you require 33 milliamperes here. A better biasing arrangement is, again, you replace the current by a transistor here. And then, of course, you can do with 3.3 milliamperes here. But a major limitation of this particular stage was we saw that if you run it at plus 3 and minus 3 here, then what happens is the output swing is compromised here. The output voltage here is VGS, one VGS drop less than whatever is the voltage here. And if this input is also coming from a circuit which is plus 3.3 and minus 3.3 here, so this can only go at as high as plus 3.3. And so the voltage here, positive swing, will be limited by at least a VGS drop here. So that was the limitation of common drain stage here, right? So in that context, we had said that let's go back then to a common source stage here. Now what I'm going to do is very quickly look at it from the point of view of efficiency. We had a little bit done. We had seen that the currents are large here and the currents are small here. Let me go back to the efficiency viewpoint here. All right. The amplifiers that we have so far talked about, both common source that you see here and common drain that you see here, we call it class A amplifiers here. And in class A amplifiers, what happens is the transistors that you see here, they are conducting all the time. Whether the voltage is positive, input voltage is positive or negative or whatever it is, the transistors are conducting, both M1 and M2. Similarly, M1 and M2 in a common drain amplifier, both are conducting. Now, if you look at if you put this requirement that all my transistors should be all the time conducting, the current may be small, the current may be large, but it's conducting. Then if I look at a particular transistor, M1, M2, or whatever you want to look at, if I look at its total current, IDS, then the total current will be made up of some bias current, plus on top of the bias current, the sinusoidal part would be riding, right? Now, if I put the restriction that my amplifier, my transistor should remain all the time, it has to remain conducting all the time. What is the limitation on my sinusoidal current then? How large can it be? Well, it's obvious that it has to, IDS, that sinusoidal current, has to be less than I bias. It has to be less than I bias. So I can write this here. So total current IDS is I bias plus IDS. And the requirement of class A operation tells that IDS here should be less than I bias. Okay. Also, then I can say the following, that my load current will always be less than the transistor current. Load current will be less than the transistor current, because note, what is the source? If I look at this, what is the source of current? The source of current is transistor M1. Like if I draw a small signal circuit, the source of current is GMVGS will be here, right? And this current divides between the load and this current here, right? So I can say that my load current will be less than my IDS of the transistor current, which is less than my I bias current here. So in effect, what I'm saying is I can claim that my load current, maximum value of sinusoidal load current can be I bias. It can't be more than I bias. Because if you try to force IL larger than I bias, your transistor will turn off. Okay. So with that, and further we also know that V0 has to be less than VDD. That also we know. Right. So these two we know that IL will be less than I bias. V0 will be less than VDD. So from here, I can get the following. The load power, note that the load power, sinusoidal load power will be equal to V0, output V0 here, multiplied by IL, and half is because of sinusoidal. Okay. So 0.5 V0 IL. So from here we see that the load power will always be less than equal to 0.5 VDD I bias here, because V0 is less than VDD and IL is less than I bias here. So my load power has to be less than this here. While the power that I take from the supply, that is equal to average power that I take from the supply. If I look at the negative supply here, the current that goes into the negative supply is here. And when we average it, we get minus VSS I bias here. VSS is negative, so it's a positive power here. Similarly, power drawn from the positive supply is also VDD into I bias. We are, of course, assuming symmetrical biasing here. VDD is VSS here. And therefore, my efficiency then, so my total power is 2 VDD times I bias. So my efficiency is less than or equal to 0.25. PL by P supply will always be less than or equal to 0.25. So the fact, without going into the details of the design, what is the biasing, what is RL and all that, we have shown you in a very general case that the class A operation is requiring this constraint to be satisfied, that IL has to be less than I bias. And of course, we know V0 is less than VDD here. And therefore, it boils down to that efficiency PL by P supply will be less than or equal to 0.25. Which means that the highest efficiency that you could design here in such a circuit is 25%. Which means what? That 75% of the power is being wasted in the transistors here. Wasted in the transistors here. M2 and M1 is wasted here, and only 25% is delivered here. So that's a major problem with this particular amplifier. That most of the power that you see here is not delivered to the load, is all lost here. Right? So it's a highly inefficient stage here. Another, you see a lot of peculiarities of this particular stage here. Suppose I don't apply any input. All right. So, sometimes, for example, let's say this is an audio amplifier. Sometimes you are speaking into the microphone, and so there's a signal here. And sometimes you're not speaking, and then obviously there's no signal here. When there's no signal here, obviously when Vs is 0, V0 is also equal to 0. No power is being delivered to the load, but your circuit is still drawing power from the supply here. Circuit is still drawing power from the supply, even though you don't have to deliver anything to the load here. So obviously one of the features that you want is you should take power from the supply only when you have something to deliver to the load. If you don't want to deliver anything to the load, why are you drawing anything from the supply here? Right? So that's, you see that what this circuit has is what we call as a standby power. Even when the circuit is not supposed to be working, not delivering any power, it has a very high standby power. The other thing is, interestingly, normally you find that if you have to work, you get hot, right? You expend energy, right? But if you look at these transistors, when are these transistors hot? When are they hot? See, when I don't apply any signal here, power taken from the supply is fixed, okay? It is this power here. Power taken from the supply is fixed. When I don't apply any input, where is that power going? Well, let's say it's dissipated here and here. For simplicity, let's say half is dissipated here and half is dissipated here. And obviously, the transistors heat is getting dissipated. Is depending on the size and other things, that transistor would be a little hot. Depending on the power, temperatures may even reach 60, 70 degrees or so. So it's hot here. Now I'm asking my amplifier to work. Work means deliver to the power to the load here. Now signal comes in and is delivering power to the load here. What happens to the transistors? they become a little cooler, right? Because some of the power that was earlier being dissipated in M2 and M1 now actually goes to the load here. So the transistor temperature actually drops, right? It should be the other way around. When nothing is being delivered to the load, my transistors should be, cool. They're not supposed to be working, and they should be quiet, and the temperature should be low here. But when it's working and is delivering power to the load, it's actually getting cooler here. All right. So you're saying that this circuit has not been designed keeping in mind efficiency. A common source amplifier that you see is primarily a gain stage for building up large voltage gain. It's not meant for delivering power to the load here. Now, keeping this in mind, now one of the things that I've told you is, if I were to design a efficient amplifier, then one of the characteristics that this amplifier must have is, when there is no input, it should not take any power from the load, from the supply. It must have that feature, which means standby power is 0. Right? When there is no input, it should not draw any power from the supply here. The other one, of course, is when there is an input, when it is supplying power, it should take as little power as possible from the supply as possible here. Right? So these are the two features that we are seeing here. So let me start with the objective of, suppose I want to build an amplifier such that when there is no input, it doesn't take any power from the supply. Suppose I start with that objective. All right, which means standby power is 0. So how would I do that? Okay, so I'm looking for an amplifier with negligible standby power dissipation. All right, so this one has a standby power here. Now remember, anytime I have an I bias, I will have a standby power. Right? Because if I have an I bias, it shows that it is biased at some non-zero current. And biasing actually means that when you are not applying any input, there is a certain amount of current flowing. So if I want to design an amplifier with a 0 standby power, what do I have to do to I bias? I have to put 0. There has to be no I bias current here. Now, so which means then consider the following. Bias current must be 0. So how about this amplifier? Let's look at this stage here. All right. Let me make it simple. Suppose I put V bias 1 equal to 0. No voltage. Nothing is there in this particular one. No bias. This is, I have not applied any bias. There is no input. If there is no input, the gate is ground. And this circuit, of course, V0, then there's nothing flowing here. There's no source here that you see here because the transistor M1 will not be conducting here. Okay. So now what will happen is, right. So let's look at Vin. Vin is not there at moment. So transistor is not conducting M1, right? There's no I bias here. Now when Vin goes positive, when it goes positive, is there a possibility of M1 conducting? Vin goes positive. Vin goes positive. This goes even higher. There's no possibility of conducting here. When Vin goes negative, then there's a possibility of it conducting here. So if I look at positive cycle, nothing will conduct. But if I look at negative cycle, if I make this voltage, initially there's no current here, this is 0. If I make this voltage below Vt, right? So for a while in the negative cycle, you see it doesn't conduct. Once the voltage here, Vin, goes below Vt, right? Then it starts conducting. And because now you see once it starts conducting here, what we have is basically a common drain stage, right? This is a common drain stage here. So once it starts conducting, so note that the relationship between V0 and Vin is V0 is equal to Vin plus Vt, right? Vin plus VGS basically here. So this voltage is VGS higher than Vin. So once the transistor starts conducting, V0 actually starts following Vin. Okay, means it starts following here. So once it starts conducting, then this becomes like a common drain stage here. And in common drain stage, V0 follows Vin. Once it turns on, all right. So once it turns on, it starts following it. And of course, it will turn off before my negative cycle is actually finished. Okay, so it will turn off here. So what happens is now if I look at this particular stage here, my positive cycle is missing. My negative cycle is, it doesn't conduct for a while. And then, till about Vt or so, then starts conducting. And then before Vt is reached here, it again switches off. All right. Obviously, it's not a good amplifier. It has heavy distortion. But what about efficiency? It has two positive features. One is doesn't have any standby power, right? And the other one is let's calculate the efficiency of this one here. So if I want to calculate efficiency, power delivered to the load will be 1 by T IDS square times dt. Okay. IDS is, we are assuming it's not a perfect, even this one is not a perfect sinusoid, but I'm just ignoring for a moment this part here. Okay, so I'm assuming this is a half sinusoid with a maximum value of IDS max here. So you can PL, you can write as I square ds max times RL divided by 4. It's a simple integral that you do here, sinusoid. Okay, so that's the power delivered to the load. Power taken from the supply here will be 1 over T VSS into IDS dt here. And IDS is what? Half sinusoid again. Okay, so half sinusoid. So you integrate that, you get VSS into IDS max, whatever is this maximum value, divided by pi. All right, so that's the half sinusoid integral, average value of a half sinusoid. And this is the average value of square of half sinusoid. Okay, so that's these two. So let's take the ratio PL by PSS here. So when I take the ratio, I get efficiency. Efficiency turns out to be pi by 4 IDS max into RL divided by VSS. And IDS max into RL is nothing but V0 max. So I can write it as pi by 4 is nothing but 78.5, and we write it as V0 max by VSS. So what it is showing you is if you drive it hard, V0 can become close to VSS within a saturation voltage drop or so, can become that. And therefore, you can get efficiency which is, greater than 70%. So you get fairly high efficiency. Earlier we were talking about an efficiency of only 25%, and now here is an amplifier stage which is potentially doesn't have any standby power and is giving you a efficiency as high as 78% or so, right? But what is the drawback? Well, my positive cycle is missing. So all the information above 0 is missing here, right? So it's not good from that point of view. But I'm sure now you can see what the solution is. Yeah. Vin. No, now remember the signal has been built in to a large amplitude by the previous stages, right? So and therefore the signal is already maybe at +2 or +3 and -3 by the previous stage here, and then is being applied here. It's no longer a very small. This is an output stage. Okay. So this is the stage which gives us a negative cycle here. Now I'm sure if you can think of a complementary stage here. This one and this one will give me positive cycle here, because this one will conduct only for when voltage becomes larger than Vt here, and then therefore the natural solution is combine them together here. Combine them together. Now I'm deliberately putting here, if you go back and see, I'm deliberately putting a bias voltage here. Why? Because note that what I was saying is if I don't put any bias voltage, my Vin has to be larger than Vt. Now what I can do is using my bias voltage, I can bias it very close to threshold. Very close to threshold. And then what will happen is this point will not have to be there. It will immediately start conducting in the negative cycle here. So just for the sake of generality, I've kept the bias voltage here. All right. So we get, this gives me positive cycle, this gives me negative cycle, combine both of them together, and this will give me a positive and a negative cycle here. Now an amplifier in which the transistor conducts for only half the cycle is what we call as a class B operation. for 180 degree, only positive cycle or negative cycle here. So it conducts for 180 degrees rather than full 360 degrees. And we call such an operation as class B operation here. So we end up with an amplifier here, which we call as a class B push-pull amplifier. All right. Now this class B push-pull amplifier has been built using a common drain stage that you see here. This is a common drain because you're taking output at the source here. Now, so how does it work? Well, in the positive cycle here, what will happen is this transistor will conduct and it will push current into the load. Okay, that's where the word push is. It's pushing current into the load here. Negative cycle, M1 now turns on and it pulls current from the load here. It pulls it into itself. So it pulls the current into itself, and we call this as a class B push-pull amplifier. Okay, and and this particular amplifier will obviously have very high, it has negligible standby power and it has very high efficiency. Okay, all right, let me show you some examples here. So this is some simulation results. Let me show you. I've taken a fairly large size here, 700 by 1, 700 by 1 here. This is what you end up with. This is my input. So I'm giving an input. Red one is an input, which is +2 and -2. And what you see here is the output here. The output, when I go positive, this is supposed to work, right? This is supposed to turn it on. It doesn't turn on until I reach some 0.7 or so. Then after that it turns on and it starts following it. But there's a difference between the input and the output. Why? VGS drop has to be there. So if this is around 2, note that this is something like maybe 1.1 or something like that. Some kind of a VT or so drop is there here. Okay, a little bit larger than VT drop here. And then again it turns off here. Then this transistor turns on and negative, and then that's what you see here, right? So the problem, of course, is this one here. This one problem here. And we call this particular problem as crossover distortion. There's a distortion when my signal is crossing 0. Otherwise, the signal is pretty okay, right? So, and let me show you, if I do a harmonic analysis of this waveform, this is what I find here. Look at the signal here. It shows me my fundamental frequency was 1K. Doesn't show much at 2K. It shows at 3K, shows as 5K and 7K odd harmonics. Because it's a 0 crossing distortion here, so it shows up as a odd harmonic. And the total, if I add up all the harmonic distortion, the total harmonic distortion is very large, 22% or so. Very high distortion, which means that I can't simply have a stage like this. I have to solve this particular problem. And how do I solve this particular problem? Well, instead of 0 volt, I add here maybe about a VT drop here. And here I add about another similar VT of this particular transistor. So let me do that here. So I added 0.7. I've taken a very simple case. M1, M2 are all symmetrical. VT is around 0.7. So I added that here, 0.7 and 0.7. Now you see the input is shown in red and the output is blue, and very good sinusoid here. Distortion, look at that. The moment I do this, my total distortion has become less than 2%. From 22% it has become 2% here, distortion here. But what is the price that I pay? Because I put 0.7 and minus 0.7, there is a standby power. I will have certain, threshold doesn't mean 0 current. Threshold means that there is a current here. So I have a standby power, and I've written here 24 microwatts here. And also, if I calculate efficiency here, efficiency is 49.1%. Now efficiency is not that high, 78, because note that I'm driving it only till about 2.4. Efficiency rises with the voltage that you drive. Okay. If I drive it higher, note that it depends on the voltage here. If I drive it stronger to 3 volt, I apply something here so that it goes up to 3. Efficiency climbs up to 71.6% here. Okay. It doesn't go to 78.5 because V0 max is not equal to 3. And plus because there's standby power and all that. Okay. So that's what we end up getting here. If you want to reduce distortion even further, if you're not happy with 2%, what you do is you increase this bias voltage a little more. So I made it 0.8. Now the distortion, look at that. Distortion has become less than 20 milli. It's just practically disappeared. Standby power. Note that this was 24 microwatts of standby power was there. Standby power is 2.92 milliwatts. So that's the price that you're paying. If you want to get very low distortion, then you have to bias it a little bit above threshold, and those standby power increases. My efficiency falls to about 68% at 3 volt here. Earlier it was 71.6% here. So I'm paying the price of efficiency. Efficiency is standby power in order to reduce distortion to a negligible value. All right. This one just shows there are more simulation results. They show how the current flows here. This one shows, for example, the red one shows that my transistor M2 is turning on. Right? M2 is turning on, and then after M2 turns off, then M1 turns on. Now, when I put 0 and 0, note the two transistors are never overlapping. Either M2 is on or M1 is on, and therefore there's no standby power. When I make 0.7, just when M1 switches off, M2 turns on. Again, there's hardly any standby power. But then when I make it a little larger here, now note that before M1 switches off, the M2 is switching on here. There's a path here, direct. Right? There's a direct path from positive supply to the negative supply here. All right. You get a direct path here. And so you start getting more and more standby power problem here. Okay. So that shows you how the currents are going. So this is the ideal situation that we want here. Okay. But you end up with getting a little bit of distortion here. All right. Distortion can also be reduced by negative feedback. So in this case, I'm just showing you an amplifier where I've not put any those voltages that you saw, biasing it at close to threshold here, and put a negative feedback. And negative feedback also corrects it, even without putting any batteries. Anyway, I'll wait for a moment here. Okay, so these I'll skip here for a moment. These are different. Now I'm taking body effect into account and all of that, so I'll skip. But these are more details. Let me skip here and come to a classAB push-pull amplifier, which is now built using common source stage. I need not use common drain. I can use also a common source stage here, right? So it's a similar one. So what I do again is, when I don't apply any input 0, I want my transistor M2 to be off. So which means, what do I need to apply here? See, this is 3.3. Vin is 0. So I need to apply a voltage which is 3.3 minus Vt. Right, so 3.3 minus Vt, Vt is about 0.7, so I need to apply 2.5 or 2.6, right? So I need to apply here 2.6 volt here, and that 2.6 will keep M2 just at the threshold. Similarly, I need to apply minus 2.6 or whatever to keep M1 just at the threshold. So I need these batteries to keep M2 and M1 just at the threshold, very close to the threshold. And when Vin comes, when I have positive Vin, what will happen? Positive Vin, M2 will, further go into off state, and M1 will turn on. So what happens is, during positive, M1 turns on and pulls the current in. And during negative, M2 will turn on and will drive the current in. All right. So that's also a class AB. Now, okay, I didn't tell. Class B is when the transistors are conducting only for 180 degree. But when I bias it a little bit above threshold, the transistors are conducting for more than 180 degree, right? So if you go back here, to this one here, this part here, right? If you look at this one, the transistor is conducting for more than 180 degree here. So that's a class AB operation. It's not class A. Class A conducts all the time. Class B conducts only for 180 degree. This conducts for more than 180 degrees. So we call it class AB operation. Okay, so that's a class AB push-pull amplifier using common source stage here. Now, this is the same thing that happens here when I just bias it at threshold, 2.6 here and minus 2.6 here. You see there's a distortion here still. There's a distortion here. So I need to bias it a little bit higher here. And when I do that, note that next thing I did 2.5 here and minus 2.5 here. Now I have a much better waveform here. So as usual, if I do 2.5 here and minus 2.5 here, there would be a standby power. So that's the price. Again, the same thing that you have to do here. Okay. So this is with 2.5 and minus 2.5 here. So you see here and you see here, the before transistor M2, let's say, switches off, M1 is also turning on. So you have to do a class AB operation sort of thing in order to get low distortion here. If you try to do class B, where the two currents don't overlap, then of course you end up getting a crossover distortion. Okay. All right. The next issue is, all right, so we know now that we can build a class AB stage here. And the advantage of this stage, of course, is that V0 can go up to VDD and can go up to VSS here. Okay, so it's a class AB based on common source amplifier. So it has the advantage of swing also. That based on common drain had a problem of swing. Okay, now the issue is we have to realize V bias 1 and V bias 2. All right, and remember the signal for this amplifier will come from a previous stage, which is nothing but, let's say, a gain stage here, a common source amplifier of this kind here. So now the issue is, remember this common source amplifier that we have here, previous stage, we are going to design it such that the normal biasing point here is V0 is 0. Right? Normal biasing is 0 here. That's what we've been talking about. A common source stage, active stage here. This is 0. Now, and this will drive my class AB amplifier here. So I have to connect it here. Which means that I have to realize a battery of about 2.5 volt. And similarly, I have to realize a battery of minus 2.5 volt. And these batteries are, note, some sort of a floating battery here. Floating in the sense both nodes are, both nodes are floating. One of the nodes is not ground. So I have to realize this V bias 1 and V bias 2. And these are, non-trivial things, realizing this V bias and V bias 2. Let me show you a possibility, how one may do that. Okay, so I need to realize this in order to complete my class AB stage here. All right. So what I'm looking for is this voltage to be approximately VDD minus 0.7. Okay. And this voltage to be minus VSS plus 0.7. Just bias at the threshold. You can increase it to 0.8 and 0.8 also. All right. So right now, let's just say minus 0.7 and plus 0.7. This is what I'm looking for. So I do the following. Look at this one. So I'm trying to realize V bias 2 and V bias 1. What will this V bias 2 and V bias 1 will do? Suppose this is 0, right? If this is 0 for a moment, input is 0 here. This V bias 2 will cause a biasing of this particular transistor by 0.7. And similarly will cause a biasing of this by 0.7. What is this goal? What is the goal of 0.7? To cause a little bit of current to flow through this, right? Little bit of current to flow through M2 and M1, right? So the transistor is on. Okay. Same thing that I'm doing here. If you look at, now you will say, well, how will you generate V bias 3 and V bias 4? But V bias 3 and V bias 4, we may do that. It's not a floating battery. Okay. So suppose I have V bias 3 here. And so I adjust V bias 3 so that this is 0. Okay, this is 0. And I adjust V bias 3. So what it will do is it will cause some current to flow here. Alright. And now the same current will flow through this one also. Now depending on the ratio of the sizes here, I can arrange whatever current I want here. Whatever current I want it to be biased. Say I want it to be biased at 10 microamperes. Right. So I can either adjust current here. Note the output transistors are much larger in size, okay, because they have to drive the load. You don't want other transistors to be larger. So let's say this is 100 micron, okay, 100 micron in size. This is 10 micron. So what I will do is if I want 10 microamperes current to flow here, I will cause 1 microampere to flow here. So 1 microamperes here and the ratios are in 10:1. So my 100 microamperes will, or 10 microamperes will flow here. So the idea is that I use a stage like this and V bias 3 and V bias 4 will cause appropriate amount of current to flow in this and this transistor and thereby keep M2 and M1 biased at close to threshold. Okay, so that's the idea. But then note this has to be connected to the previous stage. previous stage is nothing but here, and you can see a problem because this is a gain stage, and gain stage, if I just connect it here, what happens? If I just connect it here, remember earlier the resistance was R01 parallel R02. Now at this stage, when I look into here, what do I see? 1 over GM. 1 over GM. So my entire gain of my previous stage collapses. It's supposed to build up gain here, and the gain collapses here because of this connection. Alright. So although by choosing V bias 3 and V bias 4, I can bias this M2 and M1, it's causing a problem in interfacing here. So what we do is the following. We put another stage like this here. Okay. Here. So it was causing a problem, so we drive it through this one. Okay. So now the idea is I connect it here. So now, of course, it's seeing the gate, and therefore the gain is not affected. What does this stage look like? Common drain. Common drain stage. So some signal you develop here. This signal starts from here, up goes here, and now from here to here, it will eventually go from this point to this point here. It will go here. Okay, and will go to M1. Similarly, from here, it will go to M2 here. One can make the circuit symmetrical by doing the following. V in, where this part drives this part here, and this part drives this part here. Okay, and therefore one can get a amplifier like this here. So this is my class AB buffer stage here, red one that you see here, and this one is my common source gain stage here. Alright, this is the one which will drive here. So signal, whatever voltage you develop here goes here into this one. So once the voltage goes positive, it goes here, and from here it travels to this positive here and will turn on M15 here. Right, it will turn on M15. Once it is positive, if you go and see here, it travels from here, goes here, makes it more positive, and M14 is off. M14 turns off because positive voltage will cause M14 to turn off here. So only M15 is on. So when the signal here is positive, M15 is on. When the signal is negative, M14 is on here. Alright, so this will act like a common source gain stage along with the buffer amplifier here. Now all I have to do is develop V bias 3 and V bias 4, choose these voltages appropriately to cause the current that I want in this particular circuit. Okay, so that will take care of my class AB output stage here. Okay, now I'll not go into the details. You can think of how to bias V bias 3 and V bias 4. Now I'll not go into details of this. Let me show you some class AB buffer amplifiers taken from literature. Okay, some of the things that have been published here. Look at this one. All right, look at this amplifier. There's a full op-amp, complete op-amp. Can you recognize what is happening in these stages? Does it make sense, the circuit? All right, if not, let's look at this again. What is this? Look at this part here. So note that what will happen is, say, suppose you take 3.3 here, right? 3.3 here, and here is minus 3.3. Just for the sake of argument, let's say all NMOS and PMOSs are the same. So if all are same, how much will be the drop across each? 3.3 divided by 3. So 1.1, and 1.1 will cause how much? Some amount of current to flow. So there's nothing but a current source. It's generating the current for your, remember I said that for your circuit what you need is a reference current. And from the reference current you generate all the other currents. So these guys are not generating a very hi-fi reference current which is independent of temperature, supply and all that. The current is derived from the supply voltage itself. Okay, so from VDD and VSS, they derive the current. So some current flows here. Okay, so this is nothing but a current generator. M1, M2 and M3. Okay, simply generate. So for your op-amp also, for your assignment, if you want to generate a current, you could do a circuit like this here. You know, I said you don't have to, but if you wish, you can use M1, M2 and M3 and generate a reference current using this means here. A very simple reference current generator. Okay, not a very good reference current, but it does generate a current here. So now, so this you recognize as a current source here. What about this one? Let's focus on this one. It's a p-type differential pair with n-type current mirror load, right? And I require biasing some current here, so that is being derived from here. Okay, so that's fine. That's a normal differential pair here. Normal differential pair here. The next, what is happening is they're going to a stage like this here. Two such stages. So let's focus on these two. Two such stages are there. Each one of them is actually a common source amplifier. If you look at this one, the signal from here goes into this transistor. Is a common source amplifier with a load which is given here. Load is a little bit complicated. They have a PMOS here and another PMOS here with some kind of a negative feedback. Is complicated here because with this load they want to generate the bias also for this circuit here. Alright, so I'm not, as I said, I'm not going into the details. You can take the circuit, do some simulation and understand it better. So each one, what it does is, it's a common source amplifier here, right? Common source amplifier. And here, and what it does is, it develops a signal here and develops also a bias for M15. So what happens is, the signal that you have here gets amplified and appears over here. Okay, common source amplifier, and through this goes into M50. And this circuit here that you see here also generates a bias for M50. Similarly, you have this stage here. This stage also goes here, and this M13 is again like a common source amplifier, but something is connected to M14. M14 is a transistor, it acts like a resistor. So you have M13, which is an NMOS with a resistor in this. So it's a common source amplifier with degenerating resistor here, and this is the load here. Okay, this is the load here, and from here this is the load M12 here. So it develops a voltage here, and this is also used to bias M16 here. So the signal goes into this particular one, and then it travels here. And these are nothing but compensation capacitance here with a zero cancelling resistor, compensation capacitance, because they've used two common source stage here. One source stage here which couples into M15, another common source stage here which couples into M16 here. And this is something interesting that they've used as a load which also helps in biasing M15 here. Okay, so that's a full op amp that you see here, a differential pair, a common source gain stage plus a this thing here. Of course, you need to analyze this in more detail and sizing and all of that you have to see. But this is what this particular amplifier is. Okay. Alright, that's the output here. Alright, let me throw another amplifier at you. Take some time to digest it. See if you can recognize something here. You know, these circuits may look, when you look at it, it may seem complicated, but actually they're not. They're made up of blocks which you guys already know. Okay, so if you go step by step and spend some time, you can understand, you can design all of this. So, can you see here, this is again it's a current source. Okay, this part is nothing but a current source here. Because I think these guys are running it at 1.8 volts. The whole circuit is for 1.8 volts. So between VDD and ground, you have 1.8 volts. So what will happen is 0.9 will appear across M12 and 0.9 will appear across M11 and will generate some current. Okay. So this is nothing but a current generating part here. Come back here. All right. This looks complicated, but it should be familiar to you. Combined P-type and N-type, yes. So the M1 and M2 are N-type differential pair, and M3 and M4 are P-type differential pair. There is a biasing for this coming M6. There's a biasing which is coming from M5. So this is the N-type and P-type differential pair. What they're trying to do is build a wide swing differential pair that I was talking about. And remember, I was saying that to make it uniform, you have to modify the current sources. Once one differential pair switches off, you have to increase its current. So they've added all these extra circuitry for that. Okay, which we have not talked about, to make the performance uniform over the entire common mode range here. So that is what they have done. Can you recognize this? This is a cascode. See, differential pair, when you combine the two differential pairs, the differential pair must have a load. So what they've done is the load for these differential pairs, N-type and P-type differential pairs, is a cascode load, folded cascode load here. So if you note here, if I can see here, let's say M3 and M4. Can you see M3 output going here and M4 output also going here, right? Into this load here. Then what they do is M1 and M2, the currents are flowing down. And what they do is currents are flowing down. They convert it using this to make currents go in a different direction. M1, let's say M1 goes here, and then they have this PMOS, so it drives the current into it. Similarly, they have M2, it goes into M17, which helps in driving current into the load here. Remember, we said current going into the load, you have to convert it current coming out of the load. So they're doing all of that using M15 and M16 now. Okay. And so this is a wide swing differential pair. This is a folded cascode load for it. And finally, what they have is, this is the bias circuitry for your class AB stage here. Now, bias circuitry is more complicated here. They've added a common drain stage here. All right. So I will not go into the details here. They've added a common drain stage here and another common drain stage here, and then generating appropriate bias. So the signal travels from here, eventually it goes here along with the bias voltage. All this is for generating the bias, appropriate bias for M37, which is the output transistor here. All this part similar for generating bias for M38. So you have to generate a bias and you have to propagate the signal to the gate here. So that's what this part is. And the final, of course, is your normal class AB output stage here. All right. So although it may look complicated, you have to spend a little bit time analyzing how are they generating the bias here and how are they doing it. So what I'm trying to state is these are realistic amplifiers that people are using in applications. These are not, these are well within your capability to understand and design. All right. You have all the basic knowledge to do these things here. Okay. This is the amplifier that we've been talking about. I'll stop after this. Class AB amplifier. What one can do is also, one of the problems with this particular amplifier is that it has high efficiency, it has good swing, but remember it's a common source amplifier and therefore its output resistance is large, right? So what one can do is, one can build, I've hinted earlier, one can build an amplifier like this here. Look at this amplifier. Okay. So what happens is you build two what we call as error amplifiers, A1 and A2. And so the signal here goes into this and this goes here and this goes here. And you can analyze this particular amplifier and you can calculate its output resistance and show that output resistance is much smaller because of the presence of A1. And note here, if you look at this one, if you assume that the gain is sufficiently high in this loop, what will happen is V in will be equal to V out. There's a feedback loop, and in the loop, if the gain is sufficiently high, then the negative and the positive terminals become equal, and so V in becomes equal to V out here. So it acts like a common drain stage. Remember what a common drain stage is? That output follows the input. So here also, output will follow the input. That's why we are calling it a pseudo source follower. It's a source follower because a source follower is nothing but common drain amplifier where V0 follows the input, but it's actually being built using a common source amplifier with an error amplifiers that you see. Okay. Now the issue is, how do you build error amplifiers? Well, this is an error amplifier here. You need two error amplifiers, A1 and A2 that you see here. So I have an error amplifier, M1 and M2. This is a folded cascode load. Folded cascode load, it goes into M6 here. So one error amplifier with the folded cascode load goes into M6. Another error amplifier with the folded cascode load goes into M6A. All right. So what happens is you start with simple things. You say error amplifiers. You know how to build error amplifiers with folded cascode load here. This is our error amplifier with folded cascode load. All right. I'm not showing you the final circuit. This was part of an MTech thesis here. One of the students, he took a course like this, and then all I want to tell you is to give you confidence. He took a course like this and ended up designing a very nice amplifier which works on 1 volt, plus 0.5 and minus 0.5. Same 0.5 micron technology works with plus 0.5 volt and minus 0.5 volt, 1 volt amplifier here. Okay, and so this was based on something of this kind here. Okay, with error amplifiers and folded cascode. So all that I'm trying to say is you have within you now the capability, you have all the basic building blocks to begin designing these more complicated, more realistic op amps, comparators, and all of that. Okay. All right. So let me stop here and